and finally landing. And before we begin our field trip, I'd like to take a moment to let you know if you have any questions, please put them in the chat box and we'll have our tour guides, Amanda and DJ, answer them when appropriate. We are also recording this program and it will be made available only to those who registered in advance, but were maybe unable to attend. And we hope that you will enjoy this today. Now let's do our introductions to our NASA tour guides. Amanda Harvey and DJ Emmanuel will tell us about themselves and what's happening at the Goddard Space Center these days. Amanda, go ahead and start us off.
Hi, my name is Amanda Harvey. I am the program coordinator for the NASA Goddard Space Flight Center Visitor Center, and I have been with NASA for a number of years, and so I'm excited to share some information with you about what our current projects. DJ?
Yeah, hi, I'm DJ Emmanuel. I'm operations manager here at NASA Goddard Visitor Center. And I've been here 30 years. So I've seen a lot of things from the Hubble all the way up to James Webb here. We've been involved in those projects. So I'm involved with doing tours and educational programs such as this. So I hope you enjoy today's program. Thank you.
Thank you very much for inviting us to join you guys today and to share some information with you. So we are located in Greenbelt, Maryland, right outside of Washington, D.C. And today we're going to talk a little bit about an overview of Goddard itself, the center, and then we're going to look at some of the missions that we do within each of our different science areas. So we're going to look at earth science, planetary science, geophysics, and astrophysics. We'll talk about a few of our current missions going in each one of those areas. So as we go, I'm going to turn my video off because my computer sometimes gets upset when I'm trying to show the PowerPoint as well as talk at the same time. So let me hide this. So to begin with, we are going to show you this clip, this video clip to kind of give you a great introduction into our center.
At NASA Goddard, we build space telescopes.
To explore the evolution of galaxies, stars, and planets that make up our universe.
We discover planets around other stars and investigate whether they could support life and what that life might look like.
We imagine, then engineer far-out missions to answer questions about how galaxies and planets formed and evolved over time.
At NASA Goddard, we study the sun's dynamic behavior and the space weather that it generates so we can protect astronauts and satellites in space as well as our technology on the ground.
At NASA Goddard, we use the data from a constellation of satellites to generate global maps of rain and snow pummeling the Earth.
To monitor how greenhouse gases move through the atmosphere.
And to model all of the Earth systems to create a dynamic portrait of our planet.
We launch small rockets carrying university-developed experiments into space.
And provide low-cost space platforms for testing new instrument concepts and engineering techniques.
At NASA Goddard, we ensure every craft is space-ready.
We blast noise and shake instruments to simulate stresses at launch.
We expose them to the unforgiving vacuum of space and to the powerful magnetic fields.
At NASA Goddard, we develop and maintain communication links between Earth and spacecrafts in orbit.
We evaluate and improve system software to reduce risk in our missions, large and small.
Innovation and science never sleep.
And new discoveries never get old.
At NASA Goddard.
So there's definitely more going on here at Goddard than we have possibly any time to tell you about today, but I am glad that we were able to kind of give you a video to introduce you to Goddard through some of our scientists and our engineers. But to begin with, each one of these red dots represents a NASA center around the United States. So we are located here within this green circle, as you can see. And I love this map because it kind of shows that we have folks all around the country who are contributing to NASA science and NASA study and engineering, and we're loads of creative people looking for ways to explore our universe and also to explore and understand our planet even better. So this is an image of our campus here at Goddard. And right here in the middle is our integration and testing facilities. So this clean room that you see right here is the largest one in the world, and it stands at 8 stories tall. This is where we build all of our spacecraft, all of our satellites, and this entire wall that you see here on this side here is a filter, or is full of, is a whole wall of filters. And we're able to capture something that's 300 times smaller than a human hair. So it's 1,000 times cleaner than any hospital operating room, and it's a really great place for us to build things that we're sending out into space. It's very important that we keep things clean, that nothing from us ends up onto our spacecraft, so that we can protect it and protect its functionality as it's going out into space as well. And then next to that, in these white buildings right here, is our integration and testing facilities. And we do use those, excuse me, we use those facilities to make sure that we can have our satellites ready to go for launch. So this is an image inside of our clean room as well. So this is the filters I was just mentioning right here. And at this moment, this was a few years back. This is when we were building the James Webb Space Telescope here at Goddard. So it's laying on its back here. So the mirrors were being installed at this point, and the secondary mirrors up on the top here. And this is our testing facilities, as I was mentioning. So we test for 2 different excuse me, guys, I am getting over COVID, and so my brain is all squirrely, so I'm very sorry. Please forgive me. So we test for 2 different aspects when we are looking at our satellites. One, we want to make sure it can survive the launch into space. So these 2 right here test for the launch into space. This one looks at the sound to make sure that the sound of the rocket launch isn't going to cause a problem. So this is our acoustics test chamber. And we have a 3-story tall speaker in here. That's what this is. And it is massive. It is giant. It's the largest and loudest speaker I've ever experienced in my entire life. So we put our satellites into this room. We seal the doors up, and then we blast the sound of a rocket launch at it to make sure that the vibrations from the sound don't cause any damage or cause any issues with our satellites or our software or anything on board the satellite. And then we test to make sure just the general vibration of the ride up into the rocket isn't going to be a problem. So this is our vibration chamber. So we mount a metal plate onto the top of this part here, and then we mount our satellite onto that, and then we vibrate it and shake it like crazy. It's kind of like a paint mixer you might find in a home improvement store, but it's way faster. So it moves about 3,000 times each second. So 3,000 movements per second. So it's incredibly fast. And it would go side to side, front to back, all diagonals, up and down, everything you could think of, just to make sure nothing comes loose or breaks. So we can make sure that the launch, because I don't know about you guys, but if I spent like forever building a satellite, I would probably be upset if the launch is what broke my satellite. So we want to make sure that's going to be fine. Then we check to make sure that the environment of space is going to be fine for our satellite and that everything's going to work and function just properly. So this is our space environment simulator. This is a giant thermal vacuum chamber. This top part here slides off. We lower our satellites inside. We close the top. We seal it all up. And then these cylinders around the outside pump out all of the air to mimic and create the vacuum of space here on Earth. So we can test to make sure that the absence of air doesn't impact how our satellites function. We then, so it's a thermal vacuum chamber, so we can heat it up to about 350 degrees or so for a long period of time so that we can make sure that the extreme heat of space won't cause a problem. We then also cool it down to about -400 degrees Fahrenheit for another several weeks at a time to make sure that the extreme cold doesn't impact the functionality of our satellites as well. So we do all this testing, and it's definitely a very unique ability that we can do a mission from start to finish. We can imagine it, we can engineer it, we can create it in our clean rooms, and then we can test it. And then on our facility on the coast at Wallops Flight Facility, we can launch it. So we can do a mission from start to finish, which is really unique. All right, so these are the 4 science areas that we are going to talk about today. To begin with, we're going to look at our Earth science. So DJ, could you tell us about our Earth observing satellite fleet?
Sure, the NASA Goddard Space Flight Center's Earth Science Division is the largest collection of Earth scientists on the planet. NASA studies all aspects of the Earth from the vantage point of space, as well as studies that involve aircraft, ships, and scientists on the ground all over the world. The Earth observation system is made up of 23 satellites that have orbited or continue to orbit the Earth since their program began. The first of these satellites was launched on December 18, 1999. That was Terra. So over the next 10 years, we're planning to build 5 new spacecraft that will improve monitoring of the Earth's changing climate. We're going to measure some of the planet's most complex natural events, including earthquakes, volcanic eruptions, and landslides, and collapsing ice sheets. Latest is Sentinel-6 microfile satellite, which was launched on November 21st of last year. It's a 5.5-year mission to collect data on global sea level and how our oceans are rising in response to climate change. So scientists are expected to be able to measure sea level height to within 1 inch. The mission will also collect precise data of atmospheric temperature and humidity that will help improve weather forecasts and climate models. So what you're seeing are some of the satellites, some of the slides on the other side of Earth, but we're going to concentrate on GPM and ISAT, which are on the left. So the next satellite we're going to see is the GPM. So the GPM was launched on February 27, 2014. So the GPM mission uses 9 international satellites provided by the United States, Japan, France, India, and Europe. The core of that constellation is a GPM satellite. The GPM constellation provides a global map of rain and snow falling every 30 minutes. The satellite will scan the skies between the Arctic and Antarctic Circle. The GPM microwave imager, which you see rotating at the top of the dish, operates like an X-ray. It can tell the difference between liquid water, snow, and ice. Each object, such as rain, snow, and Earth's surfaces, emits or scatters energy based on the object's temperature and physical properties. Then there's a dual frequency precipitation radar, which is what the box-like structure you see underneath the spacecraft. That operates like a CAT scan. It provides information how many raindrops of different sizes are in the cloud layers and how they're spread throughout the storm system.
So this is a video of GPM observations of Hurricane Arthur in July of 2014, and it shows what GPM can do. So just as DJ mentioned, GPM's radar cuts through the hurricane, measures the intensity and types of precipitation all the way through it. So if you note this blue colored material at the top, this is ice. And so the transition of ice to water vapor is what helps the hurricane store energy. And that's something that we didn't know before the GPM mission. So hopefully after GPM, we have a better understanding of how hurricanes develop and we can predict their paths more accurately in the future. So again, we didn't know before that the ice was what changed. So it's kind of is the potential energy within the hurricane. And so we can use that to figure out where it's going to move and where it's going to go going forward.
So another important mission that was designed and built here at Goddard is the incredible laser. So you see that green laser coming from underneath the spacecraft of ISAT-2, which is currently mapping the height and location of all the ice in the polar regions of the Earth, as well as glaciers in the mountains, and the height of trees in the Amazon, and the health of the coral reefs. So the laser can penetrate the ocean about 40 feet and look at the health of the coral reefs. We know our planet is changing faster each time we measure it, and ISAT-2, as well as our other satellites, will help us get ready for rising oceans, more extreme weather, droughts, and changes in the atmosphere. The satellite has a single green laser that is split into 6 beams as it leaves the bottom of the spacecraft. We then stopwatch, time how long it takes for that laser to reflect off the Earth's surface and back to the spacecraft, down to a billionth of a second. We can measure the thickness of the ice down to the width of a number 2 pencil. The laser sends 10,000 pulses of light each second, each pulse sending 300 trillion bright green laser photons to the ground, yet only a dozen will ever make it back to the spacecraft. We take measurements every 2.3 feet along the satellite's ground path. And knowing that the height of the spacecraft and then using GPS to know its exact location and timing how long it takes the laser to bounce back to the spacecraft, we know the thickness of the ice. And the reason why we use a green laser rather than a red laser is that it's brighter and the visibility range is longer. It also produces a crisper point or line. So all these observations, all those dots you see there, the yellows, the blues, the greens, they tell us about the temperature of the ocean, the salinity, the dust that is flying above the Earth. So with so many observations coming in from our satellite fleet, it takes one of the most powerful computers in the world to keep track of it all. We intake over 1 million observations each hour and feed the information into a computer that puts it all together, allowing us to create complex computer models to help scientists better understand the Earth's climate, of how the Earth works, from our atmosphere to ocean currents to changes on the land. These models will help us understand how the Earth works as a system. Everything is connected, the ocean, the land, the atmosphere. So what you're seeing is a model that produces a global numerical weather forecast on a routine basis. Goddard Space Flight Center is the home of the state-of-the-art supercomputer facility called the NASA Center for Climate Simulation. Goddard's high-powered supercomputer is a 15,000 processor supercomputer capable of performing a staggering 160 trillion or more calculations per second.
So this is an example of such a model where we are using it to understand how our Earth works as a system, as DJ mentioned. And as DJ mentioned, everything is connected. And so this a particular model is used to study particular particles in our atmosphere. And this is particularly looking at the Australian fires during the end of 2019 and 2020, start of 2020. So you can see the date and timestamp up here in the upper left. So what we can do is we can look at these particles in our atmosphere. We can see what's moving around. So if you look at the key on the bottom, we have carbon, sulfate, dust, sea salt, and nitrate. And we can run these observations backwards and forwards and study all aspects of the event. Hopefully it can help us to better understand how it happened and possibly how to better respond to similar events in the future. And so, as I mentioned, we can play these back and forth. We can figure out how things changed, how things didn't change, if there's regular patterns. Well, we know there's regular patterns in our atmosphere of airflow. So, it really helps to understand more about what's happening, what's going on. I think this model is also very interesting for showing other aspects as well of how our Earth is connected, because we're looking at how different industry and different things within each of our continents is impacting other areas within the globe as well. So if you're looking at industry coming out of Asia here, industry coming out of the United States and out of Europe as well. And so it moves through the air and it goes back across to other continents as well. So, we're really not in silos. And so it's sort of interesting to see that happening in effect. Another interesting thing that I like about this map is you can see the dust coming off the Sahara right here. And it is coming through the air. You can see it's blowing all over to Asia, to North America, Europe, but it's also blowing to South America as well. And we found a correlation that connects the dust from the Sahara as being a fertilizer for the Amazon rainforest. So I think that that's a kind of a cool connection as well. All right, so now we're going to move on to our planetary science missions. The first of that is our Lunar Reconnaissance Orbiter. So we are going back to the moon. We are sending humans back to the moon in 2025 is the goal with the Artemis mission. And so Mr. DJ, you want to tell us about the LRO?
So yeah, LRO was launched on June 18, 2009, and it was envisioned as the first step in the return to the moon. To study in greater detail to allow humans to go back to the moon. So we're producing a high resolution 3D map to the point we can see all the way up to the moon's surface. We also want to look for things like water. That's important for astronauts to survive a long time on the moon. And we're going to be going there not just for a few days, but longer than a few days. So more time is going to be spent on the moon than we did with the Apollo astronauts. We also want to look at the radiation environment. So we're going to go over to the South Pole. So South Pole is where we're going to actually land in 2025. So part of the LRO mission was to send an L-Cross satellite that was launched with the LRO to impact the moon following a spent fuel tank that's impacted first. So you had a fuel tank that was empty that crashed into the moon, followed by this L-Cross satellite. The debris plume that was thrown up by the empty fuel tank was studied by the L-Cross before it too crashed the moon, and the data proved there was water on the moon. So the areas that are blue are areas where there's water ice, and especially in the South Pole, there's areas where the sun doesn't shine at all in those craters. So the ice has been there for billions of years. The ice mostly came from comets that have crashed into the moon. So I'm going to go to one other interesting area, because this is the Aristarchus Plateau. So this contains an abundance of a lunar ilmenite, I-L-M-E-N-I-T-E. It's a mineral that contains oxygen, iron, and titanium. So the mineral could be used for making air to breathe and even rocket fuel. So we're looking for areas like this that we could use for making rock fuel and also for air for breathing. And the last place we're going to go is Taurus Littoral Valley. That's where the last Apollo mission, Apollo 17, landed in 1972. So with this camera, you can see how good the resolution is, because we can go all the way down to the surface and you can actually see the tracks left by the rover that was used on the Apollo mission to go further than we could by just walking. You can see the lunar lander. We're going to go down. You see the bottom stage of the lunar lander that's currently on the moon. You cannot see the flag. The flag is fallen over. It's probably bleached by the ultraviolet light coming from the sun. You see the rover. So with these maps, we now have a better atlas of the moon, better than what we had from the Apollo missions.
One of the reasons that we're so fascinated with the moon is that its surface hasn't changed for billions of years. And it really is a record of everything that's happened in our solar system. So this is a video taken by OSIRIS-REx of the asteroid Bennu. And so asteroids are another type of small body in space that are even more ancient and are remnants of, even more ancient than our moon and are remnants of the building blocks of our planets. So we're looking at the moon to see what's happened in our solar system. And we're looking towards asteroids to tell us more about what how our planets formed. So asteroids are composed of different materials. Some of them are more metallic. Some of them, such as Bennu here, so it's B-E-N-N-U, is more has more soil, more regolith, if you will. So we believe that Bennu is more clay-like, and so perhaps we believe that the presence of clay means, well, we know that the presence of clay means that there's presence of water, and so we're wondering if perhaps asteroids such as Bennu struck Earth in its formative years and helped to bring us water here on our planet. And so here at Goddard, we're leading a mission to return a pristine, unaltered sample of what conditions were like over 4 billion years ago. So in October of 2020, OSIRIS-REx flew alongside the asteroid Bennu and took a sample, and we're awaiting its return in 2023. It's on its way back here. So I'm going to show you. There we go. Okay, so this is an image of an artist rendition of OSIRIS-REx arriving onto the surface of Bennu. One of the things we did not anticipate, we thought it was more smooth like this that you see here, more beach-like, but from the previous video you can tell there's a lot of boulders and a lot of rocks. It was definitely more of a craggy surface than we anticipated. But so this arm is 11 feet long, and it would come down, or excuse me, so OSIRIS-REx came down to the surface, touched just briefly, and in that moment where it was like, boop, like I say it like it was a boop on the asteroid, if you will. So very scientific, very professional. So it came down, went boop, and like backed away. And in that moment, when it touched the surface, it blew nitrogen gas out of the arm to stir up the regolith in the soil on the surface of Bennu. And then as it did that, it pulled up or gathered up as much of that was flying around into this air filter sample gathering component. And then it backed away as quick as possible. And so as it was back, after it backed away, then this arm folded up and the sample was placed into the sample return pod here at the top. And so now that top part is on its way back here. All right, so the main reason we want to know what the ancient solar system was like is to piece together the story of the conditions that allowed life to arise. So Goddard is involved in many explorations to find life-friendly environments from Mars to the moons of our outer planets like Jupiter and Saturn. And it really may surprise you that some of the best chances for life are in the outer solar system on moons that have oceans protected by shells of ice, or places like Saturn's moon Titan. And so Saturn's moon Titan has a thick atmosphere, and it may be similar to that of ancient Earth. So we are really interested in studying Titan to understand more about what's going on. So, or what was going on in early Earth. So Goddard scientists are leading a mission called Dragonfly. And so this is a artist depiction of Dragonfly on the surface of Titan. And it's an octocopter. And so we are sending this to explore Titan and to look for signs of life. And we're anticipating it should be launching in 2026. So it's an octocopter. It's like a drone. So rather than a rover that would just go on the surface and only be able to explore a limited amount of places, this octocopter, this drone, will be able to fly to hundreds of locations around the surface of Titan to gather information, to gather samples, and to do science in the little mini labs that it has on board. Excuse me. Sorry, my throat's very itchy. Sorry, guys. And so as it moves to different locations, we have some spectrometers that are on board that can tell us about the chemical components of what's going on the surface of Titan. We also have the different, a suite of geophysical and meteorological sensors, as well as a seismometer, so that we can look and see what's going on, if there's moonquakes or what's going on under the surface of Titan, and then also what's going on in the atmosphere and what's going on around there. So hopefully that will be able to tell us a whole lot more about what's going on Titan. All right, so now we're going to talk about two of our heliophysics missions. The first is the Solar Dynamics Observatory.
Launched on February 11, 2020. So Goddard leads many missions to monitor the activity of the sun and track the material it throws out into the solar system. For the last 12 years, the Solar Dynamics Observatory has returned continuous ultra-high resolution images of the sun. High-speed cameras on SDO take rapid-fire snapshots of solar flares and other magnetic activity. We can see images of the full disk of the sun from its deep interior to the outermost layers of the solar atmosphere. We take pictures every 10 seconds, 24 hours a day, with 10 times better resolution than high-definition TV. These images are taken in ultraviolet and X-ray light, which is invisible to our eyes, but picks out the most active, hottest regions of the sun. SDO will also study the amount of energy the sun puts off in the extreme ultraviolet wavelengths. These are very short wavelengths that get absorbed very high in our atmosphere, causes the Earth's atmosphere to heat up and expand, and causes our satellites that are flying in it to fall out of orbit. So this happened in March, 23rd, 2001. The Russian space station, so it's not as big as the International Space Station, but it entered the atmosphere and was destroyed back in 2001 because it flew with the Earth's atmosphere heated up. It caused drag on the Mir space station and caused it to crash near Fiji. SDO will send down 1.5 terabytes of data per day. That's equivalent to downloading 500,000 songs. The magnetic field is also looked at. We know that this is important because we never understood the direction of the magnetic field before. And that's part of our research, is to figure out what's happening to the magnetic field. And by knowing its direction gives us another piece of information to understand where it comes from and how it gets converted into solar activity. So just Thursday, there was a solar flare on the sun, and it caused some radio blackouts over the Indian Ocean. A solar flare is a result when massive amounts of energy stored in magnetic fields suddenly are released. These explosions emit radiation that contains radio waves, X-rays, and gamma rays. So they do affect our radio communications, and also planes are flying in those areas, their communications get affected as well. So the next mission we're going to go to is the Parker Solar Probe. This is the most recent of NASA's missions to the sun. It was launched on August the 12th, 2018. So it's a 7-year mission. It's already like 3 years in its mission that will eventually bring it closer to within 4.3 million miles of the sun's surface. We've never been that close before because of the temperature. So the main objective of the Parker Solar Probe is to learn more about the solar wind, a mixture of plasma. And plasma is when the atoms get so hot that the electrons break off the atom. So now you're left with these positively charged protons and these negatively charged electrons are now floating freely. That's plasma. So we're going to study plasma, magnetic forces, and particles. The solar wind also travels at immense speeds. It leaves the sun at a speed of 500 miles a second. So we want to know, what is the source of the wind? The wind is processed by the time it reaches the Earth. So by studying it much closer to the sun, the Parker probe will be able to tell us such things as what part of the sun is providing the energy source for the wind particles and how they can accelerate to incredible high speeds. At its top speed, the Solar Parker probe will be orbiting the sun at 430,000 miles per hour. Right now, it's traveling at 363,660 miles per hour, but the fastest is 430,000 miles per hour. That's like going from New York to Philadelphia in 1 second. It was also absorbed temperatures of 2,500 degrees Fahrenheit. So Parker is protected by a heat shield, which you see at the very top, facing the sun. It consists of a 4.5-inch carbon foam with a carbon plate on top and a carbon plate underneath. The rest of the spacecraft are protected behind the shield, will experience temperatures about 84 degrees Fahrenheit. So that shields the rest of the spacecraft. The instruments on board the Solar Parker probe will map the different particles and what energies they're moving at and what type of particles they are. So we're measuring mostly the solar wind and the solar atmosphere with the spacecraft here. So we also have solar panels on the spacecraft and that are used to generate electricity. It's like, how do you keep the solar panels from not melting? Well, at the back of the solar panels, we have this series of tubes that we flow cold water through. And that's used to cool the solar panels. When the panels heat up those cold water in those tubes, that water then is released as heat. We have radiators that will dispel that heat. So that's another way we keep the spacecraft nice and cool.
So now we're going to look at 3 of our astrophysics missions. And all 3 of these do have complementary science goals in that they are all going to be exploring some of our exoplanets. So our exoplanets are just planets that are not within our solar system. The first one is TESS, the Transiting Exoplanet Survey Satellite.
Yeah, so TESS is launched on April the 18th, 2018. It's called the Terrestrial Exoplanet Survey Satellite. It's the newest exoplanet explorer that's surveying 200,000 nearby bright stars within 300 light years. A light is the distance light travels in 1 year, which is about 6 trillion miles. And light travels at the speed of 186,000 miles a second in search of exoplanets. To date, NASA has confirmed the discovery of 4,306 planets. TESS will have 4 large cameras that are arranged in a vertical strip of the sky called an observational sector. TESS looks at each observational sector for 27 days before rotating to the next one. So we've already done the northern and the southern hemisphere. TESS will use a transit method to find planets, looking for a slight dip in brightness as the planet passes in front of the star. So as the planet goes around the star, orbits a star, the amount of light coming from us is going to go down a little bit. The amount of the dip and the length of time it takes to complete tells us how big the planet is and what the orbit is. The TESS has to see 3 of the same tiny dips of light to be considered as a planet candidate. During its 2 surveys, TESS has looked for for signs of planets ranging from the size of Earth to Jupiter-sized planets. So most of the planets we discover now in terms of exoplanets are mostly Jupiter-sized planets.
All right, so the James Webb Space Telescope. So this just launched on Christmas of last year, so December 25th, 2021. And so we're all familiar with the Hubble Space Telescope and the amazing science it is doing and that it has done. So here at Goddard, we're working on Hubble's cousin. I like to call it Hubble's big bad cousin, the James Webb Space Telescope. So it was designed, built, and tested at Goddard, and it is our next big space observatory. As I mentioned, it launched this December 25th. And so we have been waiting probably about 30 years or so for this to go. So it's a lot of teamwork. We had a couple thousand people have worked on this project. And so it's just been a massive feat of science and engineering and teamwork across Goddard, across NASA centers, and internationally as well. So the mirror is 3 times wider than that of Hubble. And the Webb telescope will have the power to detect water, oxygen, organics, and possibly even signs of life in the atmospheres of exoplanets. It will also have the power to observe the stars and galaxies that are so far away that their light has taken over 12 billion years to reach us. So this will give us a glimpse of how the first structure in our universe formed and how the first stars began to shine. And we'll accomplish this by using infrared light to observe rather than just visible light. So we're very, very excited for the first science that should be coming back from this. So it has, I believe, are all the mirrors aligned now, Mr. DJ?
They're still aligning each other, the mirrors, yeah. Each mirror can move like 12.5 millimeters. So it takes like 10 days to align each one. And then after they do that, they do a little bit more alignment. It takes like 6 months to get them properly aligned.
Okay, thank you. So yeah, so they'll have a time for once they're in place, then we'll do some calibration along the years. But we have deployed and unfolded the sun shield, and it is almost to its million-mile marker point. So it's going to be a million miles away from Earth in the Lagrange 2 point. So it will orbit around the sun along with Earth rather than orbiting around Earth like Hubble is doing. So we're very excited. So the first, will probably be a couple more months before we have the first science observations coming back from James Webb. So a lot of calibration, a lot of checking to make sure that everything's in the right spot. All right, so the Nancy Grace Roman Space Telescope, the third one of our astrophysics missions we're going to talk about. And before I play the video, this is one of my favorite videos. I call this like the greatest hype video that NASA has ever made. It's very short and very to the point, but I do enjoy it very, very much. So we are getting ready to build the Nancy Grace Roman Space Telescope here at Goddard, and we'll continue our work to explore exoplanets, but we'll also explore a newly discovered phenomenon called dark energy. And we'll do this by looking out into the deep universe. So dark energy appears to be driving our universe not only to expand, but to accelerate in that expansion. And this mission, much like Hubble, may change everything we know about the origins and the ultimate fate of our universe. So it was named for the first director of astrophysics at NASA in the 1960s, Nancy Grace Roman. And she helped to lead the efforts for space-based observatories like Hubble, and now for James Webb Space Telescope, and now moving on to this telescope. And, you know, it just felt appropriate to name it after such a pioneering woman. So I'm going to play this video for you. I do love it. If you don't love it, just pretend you do. I think the part when it says like the universe will be giving us some answers along with the music, I'm always like, yes, like it's so great. So that's one of the things I very much love about this video. All right, so that was the last of the missions we're going to talk about, but I did want to sort of conclude with saying, you know, we are very much looking forward to what the future holds. We can't wait to see what the new ideas in engineering and science that our current and our next generations of scientists and engineers are going to create and discover and come up with here for NASA. All right, so I'm going to stop sharing so I can see the chat, see if there's any questions that came through or if we have any questions now.
Wow, that was really awesome and really just amazing to see all these space missions that NASA Goddard Space Flight Center or Space Centers is working on these days. I hope that if anyone has any questions, that you can go ahead and feel free to put it in the chat, and we will go ahead and have Amanda and DJ address them, and hopefully see what you have questions about.
So I know you all are alumni, but if you know any students who are still in school, or if you know anyone who is in high school that's interested, we do offer internships that start at 16 years old as well. So if that's something that you wanted to provide to your next generation of William and Mary students. So yes, the Goddard Visitor Center, we do offer tours. So we have a visitor center with exhibits that you can come visit, and we do offer tours. However, we are still closed to the public. So normally, yes, but we need to get some numbers back under wrangled before we can be open again. So DJ, if you'd like to answer this question. So with the Webb telescope getting into orbit, how often does it need to be calibrated based on changing environments?
I think it's every 14 days. They're going to do like a calibration or so. I think that's the latest so far. Because what we have worry about is that the solar wind coming from the sun, when it hits the sun shield, which protects the spacecraft from the hot temperatures, the pressure on the wing, the sun shield, which is made of Kapton, which is like metaphor, it's going to act like a sail and it's going to move it around. So every so often we have to fire our thrusters, rotate our momentum to bring it to balance. So I think it's like every 14 days that to make sure it's in its proper position, its proper orbit. And so much, I'm sure they get calibrated all the time, but the space telescope is the thing that needs to be made sure it's in the right position. I don't have the schedule when they actually calibrate the instruments.
Do you know how long it will stay stable in that position then, Mr. DJ?
As long as there's fuel on board the tanks, it will stay in that position. It's an L2 point, Lagrange point, which is 1,000,000 miles away from the Earth, actually 930,000 miles from the Earth. And it's in a location where the heat from the sun, the heat coming from the sunlight hitting the Earth and bouncing to space and the moon is blocked off by this sun shield. And that sun shield has to be facing those objects to keep the telescope cold enough to be able to see infrared light, which is heat, to be able to see the very first stars and very first galaxies that ever evolved. You know, they emit infrared light, and you want to keep that shield pointed towards the sun and the earth and moon to keep it cold enough. We had to use thrusters because that orbit is not a stable orbit. Even though it's Lagrange orbit where the gravity of all those objects cancel out where the telescope is, it still moves around. So we do have to fire thrusters to keep it in its proper location. And that uses a lot of fuel. And we've only a finite amount of fuel in the tanks. So once that fuel's gone, there's no way we can keep that sun shield blocking the heat from the earth, the sun, the moon. So it's going to be wandering. So yeah. So hopefully we can get like 20 years because the Europeans did a great job of launching into the proper into orbit, into the right direction. That we saved a lot of fuel. We didn't have to move it to where it needed to be. The launcher did that for us.
And so I did type the name intern.nasa.gov, the website where students are interested in our internships. They would all be posted there and you would apply through that portal as well.
Right, and that is intern.nasa.gov.
Yep, I typed it into the chat also.
And here's another question. I guess, from where are the Goddard built satellites launched?
So we can launch them from our launch facility on the coast of Virginia at Wallops Flight Facility. We can also launch them from Kennedy Space Center as well.
And Vandenberg, California. But that's an Air Force launch site. We launched Landsat in the pole. So most of the sites we launch in the polar orbit, North and South Pole, are launched from the West Coast.
Great. All right. And then, the comment was, I'm surprised that Lagrange, was it Lagrange?
Lagrange.
Yes, I can't pronounce that. It's
I'm
not
British.
Morphian.
There's like, I think 5 Lagrange points where the gravity from the Earth, the Moon, the Sun is balanced out at that location a million miles away from the Earth. It's not zero.
DJ, that they were surprised it wasn't more quiet and more stable at that point.
Oh, yeah. It's stable. You still had to use thrusters to keep it in its right orbit. Sorry.
So I did see a question. So for those interested in potential career at NASA, how did you get to where you are today? And what coursework did you find most useful in your roles today? So there is every type of job available, probably available at NASA. So I know it's not the easiest answer, and the most helpful answer for that, but we do have jobs, within all of our science and engineering. And then we do have positions within, our communications office. So we have a social media team, we have a video production studio, we have science writers, we have we create content for social media, we have artists, graphic designers, we have giant, massive supercomputers, we have everything you could possibly think of with NASA. And even, with human spaceflight, we also have doctors and nutritionists and chefs. So I think showing the biggest thing I can suggest for students who are interested in working with NASA in the future would be to do as much as you possibly can to show that you're interested in NASA content and NASA topics, and to get involved and show that you're involved with teamwork. And I mean, I definitely think highlighting the science and the math definitely helps for whatever aspect you're going to go into, because then you can help, even if you're in the communications office, then you can help to interpret the science for the general public as well. So I think the science and the math definitely helped. And then education courses helped me a lot as well for our programming, to kind of, particularly for our younger students, younger groups who come in, that has definitely helped to help interpret NASA for those different age audiences as well.
We even have seamstresses that actually sew. These are filmer blankets that we wrap around spacecraft to keep it from overheating the space. But the sun shield on the James Webb is made of this material. It's called Kapton, K-A-P-T-O-N. So we have even seamstresses that work at Goddard. My background was computer science.
Great. I have a question. How long do these probes and satellites and telescopes generally stay in orbit? I mean, I know it's different for each one, but can you give us an idea of how long they're usually up there in space?
Hubble's been up there for 32 years. That is very long for. So we do have satellites that's been launched in the 90s and they're still up there. So usually I would say like 10 years, 5 to 10 years, they stay up there. Again, usually we need fuel to keep it in its right orbit. So when the fuels run out, there's a way. And also gyroscopes, which are used to keep it oriented, like those spinning toy tops. If those give out, then it starts to wobble, and then it'd be impossible to command it to get data from it because the antennas, which are supposed to be facing the Earth, are not going to be pointed towards Earth, so we can't send up commands. So things like those things will limit the life of the spacecraft. But usually it's like 5 to 10 years to 30 years.
Wow, that's a long time.
We get all our sciences done by then. The major science objectives done. And then anything else is additional, is like gravy,
That's great. All right, someone asked, they used to live in the Forest Gate community next to Goddard in the 1990s. Wants to know how much has Goddard changed in the last 20 years?
Probably not too much entirely. I think just recently it's changed a little more, like we're going to be moving the main gate to another location, but it's pretty steadfast. They've added a couple of buildings, but what would you say, Mr. DJ?
Yeah, and we've taken some buildings away. We've been like looking at some buildings that are really old that we never used. So to cut down maintenance costs, we've now brought them down, raised them. We got now, it's more like a campus. It's always designed, the master plan, which was a while back, was to make Goddard more of a campus-like environment, conducive to for scientists to come and do more research. We a lot of green spaces. We have a lot of green buildings as well, green LEED buildings that we're building now. The old buildings were probably not well built. So we're now raising them and building new buildings to replace them, but environmentally safe. So our footprint is getting smaller and smaller. And any buildings, we actually are bringing the fence inside. The fence is on the outside, we're bringing the fence inside. Any buildings that are now outside the fence are now probably given to other contractors, other vendors to use that work with Goddard. So we're trying to be more efficient in the space that we have.
Great.
Question says, what happens when a satellite runs out of fuel? Does it fall from the sky, float off into orbit, or keep orbiting but stop transmitting? So a couple different things they can do when a satellite runs out of fuel. So one of those is they can use the last bits of fuel to steer it and direct it so that it comes down through our atmosphere and it'll burn up in our atmosphere or crash down. Or it can continue to orbit. We have an orbit layer called the graveyard orbit, basically, or nicknamed graveyard orbit, where we'll put satellites up that are no longer functioning as well. And we try not to have them just fly off into outer space to avoid as much space junk. So we have like our layer of space junk around the Earth, if you will.
And I have a follow-up question for that. How does when something doesn't stop or stops working or needs a repair on a satellite or a probe, how does that get handled, or does it get brought back somehow?
So they try to do as much as they can remotely to try and fix it, but a lot of times there aren't things that we can do. And so we are working on some missions to provide some satellite servicing missions as well. So it's kind of like a tugboat to pull it into another orbit, or to provide it with fuel, or to use a robotic arm to try and fix it in the future. But so a lot of times we'll have redundancies on a satellite as well. So we'll have two different computers. So if one computer stops, another computer will go. Or like DJ mentioned, we'll do the initial science mission, but then if part of it fails, but then we can still use other parts of it as well. We can continue surveying that way as well.
Right.
And so I guess somebody asked as well, do we have any projects underway to clean up all the space junk? So Mr. DJ, do you want to answer that?
Yes, we're working with the European Space Agency on ways to bring back space junk. One of the things we could do is actually, as Amanda was saying about satellite servicing missions, if a spacecraft is stopped working, we can actually send up like a tow truck, another spacecraft that will go and grab it, dock it, join them together, and use the rocket engine on that tow truck to fire it into the ocean, let go of it and push it towards the ocean, or service it. They're looking at different ways to add like ribbons to the spacecraft that's needs to be brought down that will cause it to drag. As it flies into space, it will cause some drag and cause it to lower its orbit and crash. So there are ways that we're looking at to bring back, space debris. I think there was one about a net where you can actually, like a fish net, that you can throw out and grab the debris, and then the space that has a net will be firing its engine to bring everything back down into the ocean.
That's great. Yeah, there's probably a lot of stuff out there floating around.
There's, yes.
Are there any other questions that anyone wants to ask? You can also unmute yourself if you want. Oh, someone's asking, what about pushing debris up, or would the gravitational pull be too great?
But pushing the debris up, we won't bring all that stuff down into the ocean. We don't want to leave more stuff up there. It's already crowded.
Maybe
we have our our graveyard orbit, so it's a higher orbit.
Yeah.
So we do kind of push it up a bit so that it can orbit around with our other non-functioning items in the debris.
True.
Well, we're getting close to the end of the hour. So if anyone, someone asked, how much space junk is there? Good question.
Oh, give me one
I
second.
remember the number off the top of my head. I know there are several thousand pieces of non-functional spacecraft orbiting around the Earth. I can't remember the number off the top of my head, though. So yes, there are opportunities for recent college graduates to get experience at Goddard. So some of those are through we have our internships. We also have like postdocs. We have our different kind of lines along that way. We have a Pathways intern program as well. So that's something that another way that people can get experience and involved.
So I don't have the latest. As of April of 2021, there's 15,457 objects, debris right now, but that's gone up because there's just about a launch almost every day of the week. There's a lot of launches from not just the United States, from China, from Russia, from South America. So there's
DJ, could you tell us some more about the coordination NASA has with the international community?
Yeah, we work with the European, especially the ISS, International Space Station. We have astronauts from 19 different countries are on board that have been on board the space station. So we work with them on the space station. You work with other international community. We do sometimes our testing of our different parts of the site in Norway. There's a test facility out there, just like our test facility at Goddard. So we work with them in different ways. We a lot of scientists that were involved with building some of the instruments that are on James Webb. They get rights to use the James Webb for their science work. So we work a lot with the international community, especially with the Europeans and the Canadians, the Japanese, and we work with the Russians as well. But yeah, we do work with them on the International Space Station, the James Webb. We worked with the 14 countries from Europe on helping design and plan the different science proposals on the web. So yeah. And even in India has a space agency called the Indian Space Research Organization. When they build satellites, it includes some NASA experiments on them. So we try to piggyback our experiments on other satellites from other nations.
We do provide support for newly forming space organizations like the Indian Space Program as well. So we provide some mentorship and guidance to help get them going as well.
We have a comment from one of our attendees that NASA has the best education programs ever. They don't think that they get enough credit for that. So it's really great that you shared some of these things with us.
Yeah, definitely.
Thank you.
I'm happy to.
Oh, there's one more question. Are we absolutely sure that dark matter exists, or are other plausible explanations still alive? Want to take that on?
The dark matter does exist because the way the universe is structured, it cannot be just matter that we can see that causes matter to come together because of gravity. There's dark matter which we can't see, but has gravitational that has gravity that causes the visible matter to come together. So I'm not quite sure if I said that right, but yes, there is dark matter because we're studying the effects of the gravity on visible matter. Because a lot of the structures in the universe shouldn't be like it is, because there's just not enough visible matter to cause that, the gravity to cause them to form those shapes. So that's got to be invisible matter.
I'm sure it's a fascinating subject.
It is.
Sure. Well, I guess we are getting close to the end of the hour, so I'd like to, if you'd like to give a shout out to Amanda and DJ for being great tour guides for us today, feel free to put that in the chat. Thanks so much for sharing the exciting and interesting work that NASA has been doing and giving us a glimpse of what you'll find at the Goddard Space Flight Center in Greenbelt, Maryland. I don't know about you all, but I can't wait until it's open to visitors again. I definitely want to go and see it all in person. I know that one thing that I learned, or one thing that really sparked my interest, was the Parker space probe. I had no idea we had a space probe going that close to the sun to study more about it. And I think that's really fascinating. And now I want to thank all of you for taking time out of your day to spend it learning about this wonderful space center located just off the Capitol Beltway. I hope you enjoyed this virtual field trip. We look forward to having you join us at future alumni events, both live and virtual in the not so distant future. Have a great weekend and happy Friday, everyone. Thanks.
Bye, everybody. Thank you. Bye.
Bye.